Okay, so welcome back. Um, I hope everyone enjoyed the Bob Ross music. Um, so, oh, I wrote lecture 15 here instead of Math 241. This is changing it up. Okay, so last time I had mentioned um, continuity, right? Was the thing that I had left you with, the notion of a function of several variables being continuous. Now, that's we're not going to be worried too much about these things like at the foundational level, because all the functions that we're going to be dealing with are going to be nice enough. They're at least going to be continuous, and most of them are going to at least be differentiable. And that is, of course, the direction I hinted that we were going here, where we wanted to be able to talk about derivatives. And in order to talk about derivatives, you have to be able to talk about limits. So really, what I want to define is the notion of the derivative, right? So df of xy. Okay, this is what I want to be able to talk about. Okay, so and the reason, of course, I'm using quotes here is because there's no ambiguity whenever I want to discuss, um, you know, df, say dx, right? As you might write the derivative of a function of one variable. So if I have a function of a single variable, f of x, then of course discussing the derivative at a point is fine. In fact, derivatives are defined pointwise, right? And so we know what this means, or even better, if I'm talking about the derivative at a single point, maybe I'll call it point x naught, then we know what this means. But here, we don't know what this means yet. So we want to see what this means. And to do that, we recall how to define the derivative of a function of a single variable at some point. So this is defined, remember, as there's a couple of equivalent definitions, right, using the difference quotient here, but this is defined in terms of a limit, and this is the limit as h goes to 0 of f of x naught plus h minus f of x naught all over h, right? And so in the early days of computing derivatives, right, at the very beginning of Calc 1, you actually computed these things, these limits, these difference quotients. You computed them by hand. You did some algebraic trickery, and then you took this limit in any way that you could, and that gave you the derivative at that point, x naught, right? And so it was this difference quotient, right, forgetting about the limit for a second, is f of x naught plus some tiny quantity is how you're supposed to be imagining this, right? Minus f of x naught all over this tiny quantity, and then you take the limit as this quantity is going to 0, right? So this is the thing that nails down what it means to add this tiny quantity. So how do I do that here, right? What should this thing be written as? So if we're doing this at a particular point, x naught, y naught, then this thing you might think should be the limit as h goes to 0 of f of x naught plus h, y naught plus h, minus f of x naught, y naught over h, right? Maybe you think that that is what it should be defined as, because that's kind of that is what's going on here. It's just now we have an h that we're adding in each slot. But this doesn't work. Okay, so doing it this way doesn't work. This doesn't give you the thing that you think it does. Okay, we'll see later how this is actually close to what we want to do, but we can't do it directly like this. Okay, we have to do something a little different. So the thing that we have to do differently is this is almost good, but we actually have to do these slots separately. Okay, and so what works is actually this same quantity, except I do the first slot. And then separately, I have a limit for the second slot. Okay. Okay. And so mechanically, what is it that's going on here? I'm actually having to do two computations. I'm having to do a computation for this first slot, and then a computation for this second slot. What are these things called? These things are called del f del x at x naught y naught. And this second one is called del f del y at x naught y naught. These are called the partial derivatives of the function f of xy. Okay. Mechanically, how do you think finding these work? Right? If I'm just looking at what's going on algebraically here, well, I'm doing, in fact, here, let's cover this up. What do I have here? Let me see. I surely have something I can use to cover this up. Well, here. Let's do it like this. Right. I have to make sure it covers it up from the camera's view, not just from my view. There we go. Okay. So, oh, but I've actually covered up the H here as well. Okay, there we go. So, if I cover up the Y slot entirely, what does this look like? This is exactly what I have up here. It's just the derivative of the X slot, where the Y slot is just this, it's just tacked on. It's just this extra thing. Okay, similarly, that's exactly what's going on down here, except it's the derivative in the Y slot, right? It's identical to this thing written up here that comes from Calc 1, right? So algebraically, what is that going to mean for how to compute these things? This is telling us that in order to compute del x, for instance, this is going to be done by treating the y slot, right, the y argument, as a constant, okay, and taking the derivative with respect to x. Similarly, to take this del y partial derivative, I'm going to hold the x slot as a constant, okay, and take the derivative with respect to y. Okay, and so there are two of these things. These are the partial derivatives of this function f of xy. So this is the partial derivative with respect to x, the partial derivative with respect to y. This symbol is called del, or the partial symbol. Okay, if you're using something like LaTeX to write math, then this is slash partial. Okay, is that right? Yeah, that's right. Okay. And so, this is the way we have to go about this. Now, before I go about actually giving some examples of computing these things, what does this mean, right, intuitively? What is it that's going on? The idea, I'll draw a picture really quickly. If I have the graph of my function out here, so here's my graph of my function f of xy, and let's say, so we have some region below, that's my domain for this function. Okay, and so in this region, I have the point x naught, y naught, right? It's hard to see that. Okay, but I have my point x naught, y naught in this region. And so the question is, what is it that's being computed at this functional value f of x naught, y naught, what is it that's being computed when I compute the x partial at x naught, y naught, or the y partial? Sorry, this is f. So what is being computed when I compute these quantities? Well, the idea is that in Calc 1, when we computed the normal, just regular old derivative, the thing that it told us, right, or among the many things that we were told by the derivative, or the value of the derivative once we computed it, it told us the rate of change at that point, right? So going back really quickly, here's my function. If I have my function f and I'm computing the derivative at this point, we'll say, what did it tell me? Well, you might say, okay, it told me the slope of the line tangent to the graph of f at that point, but that slope also represented a rate of change, right? It told me the rate of change of the graph of this function at that point, and that's all you had to say. So for instance, at this point, the rate of change is positive because the slope is positive, which means that at that point or near that point, this function is increasing, right? That was how we defined increasing and decreasing. Well, okay, that's not exactly how we defined increasing and decreasing, but it turned out that increasing and decreasing was something that that we could figure out through computing the derivative, right? So if the derivative was positive, this thing was increasing, and once the derivative flips to being negative, then this thing is decreasing, right? But regardless, the derivative was telling us the rate of change. Okay, so it turns out that for a graph like this, talking about rate of change doesn't make a whole lot of sense without some additional words that I have to toss in. Well, what additional words do I have to toss in? If I talk about rate of change at this point, so you imagine, right, this thing is some hilly region, right? So you see that in this direction it's going up, in this direction it's going down, and in these side directions it may be also sloping down, right? So what that means is if you imagine yourself standing like on this hill, and I ask you, well, what's your rate of change, right, as you are going, say, up the hill, down the hill, whatever, I have to specify a direction. Otherwise, it's not going to make any sense. Okay, why didn't I have to do that here? So again, just like this argument we had with continuity before, here there's only one dimension worth of directions that you can talk about. Right, so there's basically no room. Along this tangent line, you're either moving in this direction or you're moving in the opposite direction. Right, so once you pick an orientation, that's it. That same kind of argument though doesn't work here because there's more than one direction to move in. Okay, and so when we talk about rate of change, it really only makes sense to say rate of change with respect to some direction. Okay, so this is immediately going to lead us to something called the directional derivative, which is going to be the closest thing we get to the old school derivative we're used to from Calc 1. Okay, but we need these partials in order to define it. Okay, and what's going on here is that these partial derivatives are computing rates of change, but they're computing rates of change with respect to some primitive directions. What are those directions? Well, they're computing the rate of change in the directions indicated by the x and y axes, respectively. So at this point, I have direction that is parallel to the y-axis. I have another direction that's parallel to the x-axis. And so what is being computed is the rate of change with respect to those directions. So as you might expect, the rate of change with respect to in the direction of the x-axis is computed by the x partial, and the rate of change in the direction of the y-axis is computed by the y partial. Okay. And so that's intuitively what's going on. All right, but let's actually see some examples of how this is done, and then you'll quickly get the hang of it. Okay, and so let's do something like, let's say let f of xy be the function that is x cubed y minus y squared plus 7. Okay, So I want to compute the x partial of f at a generic point xy and the x partial of y at some generic point xy, or sorry, the y partial of f at some generic point xy. So I'm going to quickly introduce some notation here that is going to make our lives easier, and this is something that you'll see in other courses too. Another way of writing this that is a little quicker is with subscripts. So this is kind of our analog of the prime symbol. We can't use the prime symbol anymore because the prime symbol doesn't tell you what variable you're taking the derivative with respect to. Okay, so the x partial can also be written using this symbol, f sub x, x naught, y naught, and what that means is the x partial derivative. Similarly, the y partial can be written as f sub y here. Okay, and I'll do that for the second example. Okay, so then how do I take the x partial of this? So mechanically, as I said, what goes on here is I look at this expression, I am taking the derivative with respect to x. Every y showing up gets treated like a constant. Okay, and so I'm taking derivative of this thing. Remember that in Calc 1, right, when I'm taking Calc 1 style derivative, this thing is linear in the sense that it splits up across terms linearly, right? So across linear combinations of terms, I can just take the derivative of each term and sum the results. So here, the x partial of f is going to be, I'm taking the x partial, that is the derivative with respect to x, of x cubed y, treating y as a constant. And what's the derivative of that? Well, that's 3x squared y. Okay, again, we're pretending like y is a constant. And I move to the next term. The x partial of minus y squared is, well, minus y squared is a constant because we're treating y as a constant. So the derivative of that thing is 0. Moving on to the next term, the x partial of 7 is 0 because 7 is a constant. Okay, and so let me rewrite this because I screwed up my 2 there. So this is 3x squared y. Right, that's my x partial, and I'm done. Okay. All right, let's compute my y partial. So computing my y partial really quickly, taking the y partial here. So this is this first term. I'm treating x as a constant now, right? So x cubed is a constant. Taking the y partial of x cubed y, I get x cubed. Right? So I'm taking the y partial of x cubed y. The y goes away because the derivative with respect to y of y is just 1. Okay, so this is x cubed minus 2y, right? Because that's the partial derivative with respect to y of minus y squared. And the y partial of 7 is 0. And so I get x cubed minus 2y. Okay, you'll note immediately that those things, of course, are different, right? They're definitely different quantities. Okay, but in both cases, I started with a function of 2 variables. I took the x and y partial of that function, and those were 2 functions of 2 variables, you know, in their own right. Right, and that's typically how this is going to work. Okay. All right, let's do more examples of computing these partial derivatives. Okay, so I'm just going to make up some stuff. Let's do a function f of xy is, we'll say that this thing is going to be x squared cosine of xy plus, say 7 times e to the x. Okay. All right. So now I want to compute the x and y partials here. So the x partial of f, what is that? Now it can help to write this out sometimes. So this would be the x partial of this quantity x squared cosine of xy plus, I can pull the 7 out, so this is 7 times the x partial of e to the x. Right? And so I look at this expression, what do you notice? I'm taking the partial derivative with respect to x, right? So in Calc 1 world, I am pretending that this y is a constant and x is the only variable that exists. And so in the Calc 1 sense, really I'm just taking a derivative with respect to x. Okay, so I'm taking a derivative with respect to x here, but this is a derivative of a product of two functions, right? Yeah, exactly. So as chat noted, I have to use product rule here because this is a product of two functions of x. And so I use the product rule here. So this becomes the x partial of x squared, right, times cosine of xy plus x squared times the x partial of cosine of xy, right, plus 7 times e to the x, because the x partial of e to the x is just e to the x. Okay. So, continuing forth here, the x partial of x squared is 2x, of course, so this is 2x times cosine of xy plus x squared times the x partial of cosine of xy, where we're treating y as a constant. For some of these early computations, when you're treating y as a constant, it might help your brain to think about this for a second and to actually replace y with a specific number. So replace y with like 5 here, right? So think about this as the x partial derivative of cosine of 5x, right? What would that be? Well, if this were a 5x instead, this would be, so the derivative of cosine 5x with respect to x would be 5 times minus sine of 5x, right? So replicating that with a y here, what does this become? This would be minus y cosine, or sorry, sine of xy. Right. Okay, and one more. With 7 e to the x. Okay. Now, if we were doing a computation where we needed to further take partial derivatives or to do something else with this expression, then I would say you should probably simplify this. Okay, if it is simplifiable. But looking at this, when are you done, right? This is a question students always ask. When am I done? When can I stop simplifying? If you don't have anything else to do with it, right? If you're not doing any other computations with it, and if you've computed all the derivatives, then you're done. Okay, so maybe it's something nasty, maybe it's something you can't really simplify any further. This is the idea here. Okay, so you're done once you're at a point where it's no longer useful to simplify here. Okay, so that's the x partial. All right, so what about the y partial? So let's compute the y partial. So here I would have the y partial of this first term, x squared cosine of xy, plus the y partial of 7 e to the x. Okay, so I have the y partial derivative of x squared cosine of xy. But note something different happens, right? Because this is no longer a product of functions with respect to y, right? Because we're treating x as a constant. So x squared times cosine of xy, that's just like some constant times cosine of xy, right? And so I don't need to use a product rule here because this isn't a product as far as I'm concerned, right? It's not a product of things depending on y, so it doesn't count as a product. So I can actually just take the derivative of this, treating x as a constant here. So I would have x squared times, what's the derivative of cosine of xy with respect to y? So similar to here, it's going to be minus x sine of xy. So this is the chain rule, right? I'm taking the derivative of what's inside and multiplying by the derivative of what's outside with what's inside plugged in again, right? So derivative of cosine is minus sine. Derivative of xy with respect to y is x. So this is minus x sine of xy. Okay, plus 0, of course, because the y partial of 7e to the x is 0, because that is just a constant term as far as I'm concerned here. So this becomes minus x cubed sine of xy. Okay. All right, so there's a couple of examples of how to compute these partial derivatives. Now, we're going to do many, many more examples. Before we do those, I'm going to introduce a couple of other things here, like the ability to take partial derivatives of higher order, right? So, as I said before, both of these, as you'll see, are functions of x and y in their own right, which means considering them as functions of x and y, they also have partial derivatives that I can attempt to take, right? Now, if you have a function that has its partial derivatives of whatever order you like, of course, you can continue this process. Some functions may have, partial derivatives of the first order and not the second, and so on. So you might not be able to infinitely partial differentiate these functions, but you can go, as far as you can, basically. So I'll do a couple of examples of that, but the thing that's most important is that you are going to be doing this a ton for the rest of the entire course. Okay, so for the rest of the course, you're going to have to do this, and so a very important fact here. So you must perfect these computations because they are used in literally everything. Okay, so for your next exam, every single question will have you taking partial derivatives, and there's no avoiding it. For the chapter 15 material, the same is basically true. Almost everything you come across is going to have you taking partial derivatives. Okay. So you have to get this process down. You have to be able to find partial derivatives. So let's do an example of a function of 3 variables. Okay, let's do let's do 2y times the natural log of say x squared plus y squared plus z squared. Okay. So you're like, oh, well, you didn't say anything about this, right? You certainly didn't draw a picture, and so like I don't know what it is that's going on here. Well, what's going on is exactly what you would expect. I can define partial derivatives with respect to x, y, and z similarly to what I did for x and y for a function of 2 variables, and the computation of these derivatives occurs in the exact same way. In fact, intuitively, what this thing is actually computing is exactly the same. It's the rate of change in the x, y, and z directions. The only thing different now is that rather than our underlying domain being a 2-dimensional region, right? Our underlying domain here is a 3-dimensional region, and then the graph of this function lies above that 3-dimensional region, right, in a 4th dimension, okay, which I can't draw. So, how do I take these derivatives? So what's the x partial here? Well, with respect to x, this is not a product, and so really this is just 2 times y, which I'm treating as a constant, times natural log of x squared plus y squared plus z squared. So really I'm taking the derivative of the natural log of x squared plus y squared plus z squared, treating treating y and z as constants. So when I'm taking the x partial, I treat both y and z as constants here and differentiate with respect to x. So this is 2y times the derivative of natural log is 1 over x squared plus y squared plus z squared here, times the derivative of this argument with respect to x. The derivative of x squared plus y squared plus z squared with respect to x is, of course, 2x. Okay, and so this is 4xy over x squared plus y squared plus z squared. Okay, what is the y partial? So when I take the y partial here, I treat both x and z as constants. Okay, and so taking the y partial here, of course, now this is a product. I have to use the product rule here, right? And so this is taking the derivative of the first thing of 2y, I just get 2. So I get 2 times natural log of x squared plus y squared plus z squared plus 2y times the derivative of ln of x squared plus y squared plus z squared with respect to y. So this is 1 over x squared plus y squared plus z squared times 2y. Okay, and then lastly, my z partial treats both x and y as constants. And so this is, again, y is treated as constant here. So this is 2y times 1 over x squared plus y squared plus z squared. Now I'm taking the derivative of x squared plus y squared plus z squared with respect to z, so this is 2z. Okay. So that's what these three partials with respect to x, y, and z are. Okay. Okay, and so we can continue this process. So we can define f sub xx, f sub xy, f sub yy, f sub yx. Okay, what are these things? So your textbook defines the order differently than I do, I think. So, for instance, the textbook, so I'm going to define them this way. So what is f sub xy? It is the y partial of f sub x. And f sub yx is going to be the x partial of f sub y. Okay, so your textbook reverses the order of these, but we'll see why in a second that we don't actually have to worry about that. So then f sub xx is the x partial of the x partial, and f sub yy is the y partial of the y partial. Okay, sometimes you'll hear these called the pure second order partial derivatives, and these are the mixed terms. These are the mixed partials. These are second order partial derivatives. And you might say, wait, this is strange, right? In Calc 1, if I were to ask you how many first derivatives do you have? Well, you have 1. How many second derivatives do you have? Well, second derivative was the first derivative of the first derivative, right? So 1. And in every stage, you have exactly 1 derivative. But of course, this isn't going to be the case for our examples because, for instance, here we have function f of xy, and it has 2 first-order partial derivatives, one with respect to x, one with respect to y. And then looking at this, how many second-order partials does it have? 4. Right, 4. Okay. And of course, this just gets worse as you add more and more partial derivatives here. So for third-order partials, I could define those things to be partial derivatives of the second order partials, right? So I would get some weird combinations here of subscripts, and I would have to keep track of what these things mean. So we'll see that it's not quite as complicated as it might seem at first based on that. But let's do an example where we compute all of these things. So let's let f of xy be, we're just going to make up stuff here. All right, so let's do something like, let's do e to the x squared plus y squared, okay, times cosine of 3x, okay, minus x squared y cubed plus y to the 7th plus square root of pi. Okay. All right, and so what I want to do here is compute all of the second order partials. Okay. You might say, why do I need to compute second order partials? Like, what are the second order partials? Tell me. So we'll get to that. That won't be until the end of this chapter, but we'll get to that. But the point is that you need to compute them. You will need to know how to compute these quantities in order to answer all the questions that we want to ask. Okay. Now, before I can compute the second order partials, of course, I have to compute the first order partials. So let's do that first. So what is my partial with respect to x of f? Well, this is, again, I've got this stupid product with respect to x here in my first term. So what is this? And again, it can help to write this out in the early stages so that you remember what it is that's going on here. So this is the x partial of the first thing, so that's e to the x squared plus y squared, times cosine of 3x, plus e to the x squared plus y squared, right, times cosine, times the x partial of cosine of 3x. Okay, that's what I get here. Okay. In the next term, I would have minus x squared times y cubed. I'm taking the x partial of that, so this is minus 2x times y cubed. And the x partial of y to the 7th is 0, because that's constant with respect to x. And the x partial of square root of pi is also constant, so the derivative is 0, right? It's x partial 0. Okay, so then what is the x partial of e to the x squared plus y squared? This is going to be the derivative of e to the, e, forget about what's being plugged in here. E to the blah is just e to the blah, and then I'm taking the derivative of blah. Right, I'm taking the derivative of x squared plus y squared. So this is 2x times e to the x squared plus y squared times cosine of 3x. Okay. Plus e to the x squared plus y squared times the x partial of cosine of 3x is minus 3 sine of 3x. Okay. And then, of course, from this I subtract 2xy cubed. And that's my x partial. Okay. All right. So let's compute the y partial. Okay, so my y partial is, I'm taking the y partial of this thing. So again, this first term is not a product with respect to y, and so the y partial of the first term is just 2y e to the x squared plus y squared cosine of 3x. minus y partial of this term is 3x squared y squared. Right, using the power rule. The y partial of y to the 7th is plus 7y to the 6th. And the y partial of square root of pi is 0. So this is my y partial. Okay. Okay. Now I get to have fun computing partials of these things, right? So what is the first thing that I want to do? Well, first I want to compute the x partial of this. So let's do that. This is f sub xx. That is the x partial of the x partial. Okay. And so I'm going to carefully here consider what I'm doing. I have a product of two functions of x. Of course, one of the functions is itself a product, but we'll worry about that in a second. So the x partial here is, and I'm going to write it like this, this is the x partial of 2x e to the x squared plus y squared times cosine of 3x plus 2x e to the x squared plus y squared times the x partial of cosine of 3x. Right, that's the first term. And then the second term is the x, again using the product rule. This is the x partial of e to the x squared plus y squared times minus 3 sine of 3x right, plus e to the x squared plus y squared times the x partial of minus 3 sine of 3x. So that's the second term. And then the last term is the x partial of minus 2xy cubed, which is just minus 2y cubed. Okay, so I have a little bit of work to do here. All right. Question wise, cosine of 3x, part of the y partial, shouldn't it be treated as a constant? It is, right? So replace cosine of 3x with a big C, right? And trace through this y partial, and you'll see that that big C will sit right there, right? Okay. And so have a little bit of work to do here. Let me put this at the very top. Okay, so then what is my continuing on here? X partial here is, so this is going to get nasty. So this is 2 e to the x squared plus y squared, all right, plus 2x times e to the x squared plus y squared times the derivative of x squared plus y squared with respect to x. So that's 2x times 2x, right? So that's 4x squared e to the x squared plus y squared. Okay, and all of that is multiplied times cosine of 3x. Okay, and then plus 2x e to the x squared plus y squared times the x partial of cosine 3x here, which is just minus 3 sine of 3x. Okay. All right, that takes care of this expression. So now the next thing I have to deal with is the x partial of e to the x squared plus y squared, which we know by now is 2x e to the x squared plus y squared, and that's multiplied by minus 3 sine of 3x, right, plus e to the x squared plus y squared times the x partial of minus 3 sine 3x, so that is minus 9 cosine of 3x. all that minus 2y cubed. Okay, so not too great looking. We can actually combine those two middle terms to make this look a little nicer, but we're done with this. We're not doing any more computations with it, so we can leave it like that. Okay, so that's f sub xx. All right, what about f sub xy? So f sub xy, right, defined in the way that I did it, not the way that the textbook has it written down, means that I would be taking the y partial of the x partial, which I've boxed here. So this is the x partial of f. Okay, so I'm taking the y partial of that. So moving through here, the y partial of this first term, I get to avoid having to use the product rule entirely, because with respect to y, this isn't a product. There's only one term here in this product that actually involves y, and it's e to the x squared plus y squared. And so when I'm taking the y partial of this thing, I don't have to use the product rule. This is going to be, rewriting it, this is going to be 2x cosine of 3x times the derivative of e to the x squared plus y squared with respect to y. So this is times 2y e to the x squared plus y squared. Okay, so that's the derivative of the first term. The derivative of the second term with respect to y, again, I don't have to treat this as a product. I just have to differentiate this term and treat this as a constant. So this is plus 2y e to the x squared plus y squared times minus 3 sine of 3x. All right, and then the last term is minus 2xy cubed. So I'd take the derivative of that with respect to y, so this would be minus 6x squared y. Xy squared. Okay, and that is f sub xy. Okay, so let me get rid of that. Let's compute f sub yx. Actually, let's compute f sub yy first. So here's f sub y. F sub yy is the y partial of that. So f sub yy of xy is, so I'm taking the y partial of this here. Now I actually have a product with respect to y here that I have to worry about, right? So this is a product with respect to y. So I'm taking the y partial of the first thing. So I'm going to group cosine 3x with 2y here. So I'm going to write this as the y partial of 2y cosine of 3x times e to the x squared plus y squared plus, plus 2y cosine of 3x times the y partial of e to the x squared plus y squared. So that's the first term, right, taken care of by the product rule. The second term, I'm taking the derivative with respect to y here, so this is minus 6x squared y. So it would be minus 6x squared y. And the last term, that's 7y squared, 7y to the 6th. Take the derivative with respect to y, I get 7 times 6, or 42 y to the 5th. Okay. All right. So I have to simplify this a little bit by actually taking these derivatives. So the y partial of this thing is just 2 cosine of 3x times e to the x squared plus y squared. Right? That's the y partial of this expression. Plus 2y cosine 3x times the y partial of e to the x squared plus y squared, which is 2y e to the x squared plus y squared. So this is plus 4y squared cosine of 3x e to the x squared plus y squared minus 6x squared y plus 42y to the 5th. Okay, and that is my pure y, second order y partial. All right, that's f sub y. So I have one more mixed second order partial to compute. Okay, so let's do that. So maybe I'll start on a fresh page. So then the last partial that I need to compute, or this last thing I need to compute is f sub yx, okay, which is the x partial of the y partial. Okay, so here's the y partial boxed here, and I have to compute the x partial of this. Okay, so I'm going to have to use the product rule only right here. Is where I have to use the product rule. So this is going to be splitting it, and I'm going to group 2y with cosine 3x again. So this is going to be the x partial, right, of 2y cosine of 3x times e to the x squared plus y squared, plus 2y cosine 3x times the x partial of e to the x squared plus y squared. So that is the product rule computed in the first term. There's no other product rules here, but next the x partial of minus 3 x squared y squared is minus 6 x y squared. Okay, and the x partial of 7 y to the 6 is of course 0. All right, so that's it. Okay, and so what do I get here? This is going to be, the x partial of this is going to be 2y times minus 3 sine of 3x times e to the x squared plus y squared. Okay, here this is going to be the x partial of e to the x squared plus y squared, so this is plus 4xy cosine of 3x times e to the x squared plus y squared. Okay, minus 6xy squared. Okay. All right. And so I'm done here. Now, what I want to do is to compare this with f sub xy. All right. So here's f sub xy, and this is f sub yx. What do you notice? Oh, sorry, it's off the screen. So what do you notice? F sub xy is boxed up here, f sub yx is boxed down here. Well, let's just compare them term by term. So 2x cosine 3x times 2y e to the x squared plus y squared. That is, if I simplify this, this is 4xy cosine of 3x e to the x squared plus y squared, which is here. Right? So this term is 2y e to the x squared plus y squared times minus 3 sine of 3x. That's really minus 6y e to the x squared plus y squared sine of 3x. Hey, that's exactly the thing that I have here. And then lastly, minus 6xy squared. Now, here's the deal, right? I just made up this example entirely, right? I literally just randomly cooked this up, okay? And you see from the nature of this computation, right, that it's not like the stars aligned or anything. I just randomly made these expressions up. So this is pretty good, you know, this is decent, even though we've only computed a single example. If I tell you the process for me coming up with that example, and then I tell you, and then I show you, hey, we computed this, and these things end up being equal, this seems like really, really good evidence that this is how it is supposed to work. And indeed it is. In fact, here's a nice fact. It's not true. You can't just say that they're always equal, because I can cook up examples where they're not. Okay, but those examples are really, really bad. and something goes wrong with the second order partials at the points in question. So basically, if f of xy is nice, and the caveat here is that every function we encounter in this context is going to be nice, then f sub xy is equal to f sub yx. Okay? And so it actually doesn't matter what order you do those partials in. So computing the x partial, then the y partial, or computing the y partial, then the x partial. Doesn't matter. All that matters is, so it's not the order that matters. What matters is how many of each partial you took. So this also applies for third order partials, right? So f sub, right? So for instance, f sub xxy is the same as f sub xyx is the same as f sub yxx. So what matters is the number of partials with respect to whatever variable is taken rather than the order. Okay, and you can check this for, just write down some, like, polynomial functions are the easiest to check this from, or to check this for. You can write down polynomial function and actually practice that this is the case. It's good practice for computing these things. Anyway, so that is that. We are going to have plenty of practice computing these partial derivatives. So we'll continue on here Monday. I'll talk about the directional derivative and the gradient vector. So that's where we'll start on Monday. So anyway, have a good weekend, and I'll see you all on Monday.